Welcome folks, second video in our chapter on matrices, this video on matrix multiplication. So we start off defining matrix multiplication in terms of matrix vector multiplication. After seeing a couple examples and some properties, we see that, matrix multiplication can be defined as a whole bunch of matrix vector multiplications. Some of you may have seen matrix multiplication in another context, and if you have, matrix multiplication by entry will be familiar to you. We'll use that matrix multiplication by entry to derive a whole bunch of properties of matrix multiplication, some of which might be a little bit surprising. And then at the end of this section, we'll talk about a special class of matrices called Hermitian matrices that has to do with the adjoint from our last section. Okay, so here is the definition of the product of the matrix A, which is M by N, with the vector U, which has N components. So the definition of AU is a linear combination, the element U1 with the first column of A, the element U2 with the second column of A, and so on and so forth down to the element U sub N with the nth column of A. Okay, so again, when A has N columns and U has N components, then AU is well defined, and AU is a linear combination of the columns of A. So I want to point out that the size of AU, and maybe you want to pause the video and just think about this for a minute, since AU is a linear combination of the columns of U, can you see what the size of AU is going to be? Right, the size of AU, as it turns out, has to be an M vector, right? It has to be the number of rows of A. Okay, so we'll see an example of this. Here's an example. A here we see is 3 by 5. U has 5 components, so that the matrix multiplication AU is well defined. Okay, and again, I'll point out that when A is 3 by 5 and when U has 5 components, AU has 3 components. So again, AU is a linear combination of elements of columns of A. So in this case, we see that AU is 2 times the first column of A, plus 1 times the second column of A, plus minus 2 times the third column of A, plus 3 times the fourth column of A, plus minus 1 times the fifth column of A. Okay, so doing this linear combination isn't so bad, right? We can just substitute in the columns of A, the scalars from the vector U, crank it out, and here's what you should get. If you work this on the worksheet, you should get 716. Okay, as it turns out, there's a direct relationship between the vector equation AX equals B and the linear system LSAB, where A is the coefficient matrix and B is the vector of constants. So here's the theorem. The theorem is that the set of solutions to LSAB is the same as the set of solutions to the vector equation AX equals B. So if S is a set of solutions to this linear system LSA comma B, then X is in that set if and only if B is X1 times the first column of A plus X2 times the second column of A, and so on out to Xn times the nth column of A. Of course, we've just seen that this is exactly the definition of B equals AX, matrix vector multiplication. Okay, so here is the take-home message. The take-home message is that the description of the system LSA comma B can now be written as a vector equality, right? And that vector equality is AX equals B. So in other words, solutions of LSAB are the same as solutions of AX equals B. Okay, so oftentimes, instead of writing now LSA comma B, we'll instead just write this vector equation that's represented by matrix vector multiplication. Okay, so if we want to solve the linear system with coefficient matrix A and vector of constants B, we'll now instead solve the vector equation AX equals B. Okay, so here's an example. Let's go ahead and have a look at this system of linear equations, and we'll represent this linear system as a vector equation instead. I'll point out first that our system has m equals 3 equations and n equals 5 variables, so we expect our coefficient matrix A to be 3 by 5. Here's that matrix A with 3 rows and 5 columns, and then of course our vector of constants B is 9, 0, minus 3. So again, the take-home message here is that solving LS of A comma B is the same as solving AX equals B for some unknown vector x. And again, that vector x should be a vector with 5 components representing those 5 variables. Okay, here's the theorem that I'll state without proof. The proof is in the textbook and is fairly straightforward, but it is an important result that we'll use later on. So if A and B are 2 matrices such that whenever you multiply A times X, you get the same as B times X, for any X, then A and B must be the same matrix, it turns out. So again, here's the theorem stated without proof, but we'll use this later. And the key to this theorem is that X is an arbitrary element of this vector space of column vectors. Okay, so let's go ahead and talk about matrix multiplication. And again, matrix multiplication as we define it is a whole bunch of matrix vector multiplication. So here's the definition. If A is m by n and B is n by p, then it turns out that the matrix product A, B is well defined. And again, that matrix product is m by p when B has n rows. And that matrix product is defined in terms of a whole bunch of different matrix vector products, right? So the first column of the product is AB1, the second column is AB2, and so on and so forth, to the pth column, A times BP. Okay, so again, it must be that A has n columns, and B have n rows for this to be well defined. So a quick way to check is just to write A as m by n, B as n by p, and then of course AB, as it turns out, is m by p. So we make use of those outer dimensions, the number of rows of A and the number of columns of B. Okay, so here's an example of matrix multiplication. We see here that A is 3 by 5, and we see that B is 5 by 2. So AB is well defined because the number of columns of A is the same as the number of rows of B. And in fact, AB we would expect to be 3 by 2. And here are those 2 columns of A times B. The first column is A times B1, the first column of B, and the second column of AB is A times B2, which is, again, the second column of B. So when you go ahead and write this down, you know that we already computed AB1, right? That was what we did earlier. AB2 is similar. It turns out you get 23 minus 126. And when you shove those in a matrix, that, as it turns out, is the product. So let me just write that. Okay, so again, the first column of AB is A times the first column of B, and the second column of AB is A times the second column of B. So we see here that product where the first column is 716 and the second column is 23 minus 126. So I'll give you an opportunity to work on this on your own. AB. Here's an example of 2 matrices that are both 2 by 2, and we'll go ahead and compute A times B as well as B times A. So again, when you go ahead and write that out and go ahead and work through the details here on the worksheet, what you should find is that that AB is 19, 6, 3, 2, and that BA is 4, 4, 12, 7. Okay, so this is sort of interesting, and for some of us this might be the very first time that this has happened. We see that AB is not equal to BA. Okay, so we're used to the multiplication being commutative. As it turns out, that's not a property of matrix multiplication. Okay, so in fact, there are times when AB is well defined, but BA is not even defined. So for instance, in our first example, where A was 3 by 5 and B was 5 by 2, the product BA would not be defined. Now, of course, when they are both defined, it may be the case that A and B have different sizes. Okay, so of course you can't talk about matrix equality for matrices of different sizes, but even when they're the same size, it's generally true that matrix multiplication is not commutative, right? So in other words, the AB is not equal to BA. And again, for many of us, this is the first time experiencing this property. Might feel a little bit strange, but the point is here that left multiplying or right multiplying by a matrix matters, and we need to be specific about that. Okay, let's talk about matrix multiplication by entry. Again, this is perhaps a more familiar approach to matrix multiplication for those of you who have seen it before. So matrix multiplication by entry defines the element in the ith row and jth column of the product AB as a sum here, and that sum looks at the ith row of A with the jth column of B. Okay, so so again, rows of the first and columns of the second. Okay, and this is a theorem, and the way that you prove this theorem is just by writing down A times B sub j, and then we'll see that it's exactly that linear combination that we expect. Okay, so I'm gonna just have you read this theorem. However, we'll use this theorem all the time. Matrix multiplication by entry. Again, this tells us how to find an element in the ith row and jth column of a product AB based on the matrices A and B. And again, we'll use this to talk about equality and derive a whole bunch of properties. So here's an example. Let's go ahead and find the element in the second row and first column of AB, and then the element in the first row and second column of AB. So I'll start with the element in the second row and first column of AB. So by definition, the matrix product AB, the element in the second row and first column, comes from the second row of the matrix A and the first column of the matrix B. So here are those elements again, the second row of A, the first column of B, and when you crank this all out, you get exactly what we got when we did this matrix product before. It turns out that you get 1. Okay, similarly, the element in the first row and second column of the product comes from the first row of the matrix A and the second column of the matrix B, and we can crank that out too, and it turns out that what you get is 23. Okay, so not a particularly difficult computation, but perhaps maybe a little bit tedious. Okay, in any case, the way that we use this matrix multiplication by entry is to prove certain properties of matrix multiplication. So let's go ahead and start in on some of those properties. Here's the first one. Whenever you multiply a matrix by an appropriately sized 0 matrix, you get back the appropriately sized 0 matrix. And that goes for matrix multiplication on the left or the right. Okay, and I'll go through this just briefly because we see that what we get is, or the way that we prove these properties is matrix multiplication by entry. Okay, so we see again that the element in the ith row and jth column of the matrix product A times 0 is the sum of the product of the element in the ith row and kth column of A with the element of the kth row and jth column of O. right? So since each of those elements in O is itself equal to 0, right? We know that this 0 matrix has all 0 elements. We see that the element in the ith row and jth column of A times O is also 0. Therefore, A times 0 is the 0 matrix. Okay, and that works on the left or the right. And it turns out that works sort of similarly multiplying by the identity matrix, right? The identity matrix is the special matrix that you multiply by a matrix A, either on the left or the right. As long as the size is correct, you get back the matrix A. Okay, so here's another property. Let's go ahead and look at distributive property of matrix multiplication. So again, we know that multiplication on the left or right matters. However, we would expect matrix multiplication to distribute over a sum, and it does. So we'll go ahead and prove this property using matrix multiplication by entry. So we just start off with the definition of matrix multiplication by entry, the element in the ith row and jth column of the product between the matrix A and the matrix B plus C. Okay, so now we know how matrix addition is defined, right? Matrix addition is defined component-wise. So we know that we can write B plus C in the kth row and jth column as B in the kth row and jth column plus C in the kth row and jth column. Okay, so again, this step is just the definition of matrix addition, and this step is just distributive property of scalars. Now, of course, we know that the sum over a sum is the sum of the sums, so we can write this single sum as two different sums, and we see that the first sum represents matrix multiplication of A times B, and the second sum represents matrix multiplication by entry of A times C. Okay, of course, the first sum is AB, the second sum is AC, and we started with A times B plus C. Their components are equal, so we know that, that matrix multiplication by entry tells us that A times the quantity B plus C is A times B plus A times C. Okay, that works if we're multiplying on the right by a matrix D as well, as long as everything's the correct size. And there are other properties too, distributive properties of scalar multiplication and associative properties of matrix multiplication. Okay, I'll give you a chance to prove one of these properties in a minute. So it turns out if we think about our column vectors as m by 1 matrices, then the inner product is just matrix multiplication of the adjoint of the first with the second. So I won't go through this, but it's like super useful, as it turns out, to think about matrix multiplication and relate it back to an inner product. We'll see that later on. So I'll have you read the proof of this, but the inner product is a special type of matrix multiplication too, where we're looking at the adjoint of the first. Several other properties hold that are related to complex conjugation. So the first property says that the conjugate of the product is the product of the conjugates. The second property, which I'll have you prove on the worksheet, says that the transpose of a product is the product of the transposes in reverse order. This is a really important property. Maybe a little bit surprising that they go in the reverse order, but that's the way it works out. So I'll have you prove that in the worksheet. And the third property is sort of just a combination of the first two. If we remember that that the adjoint is the conjugate transpose, then it's not too surprising that the adjoint of the product is the product of the adjoints in reverse order. Okay, so the last thing to talk about in this section is Hermitian matrices. They're pretty special. We'll talk about matrix multiplication and the adjoint in terms of the inner product. So This, as it turns out, is an important theorem that's pretty straightforward to prove. So the inner product of the vector ax with the vector y turns out to be the inner product of x with the vector a adjoint y. So we'll see this just by the definition of inner product as matrix multiplication. Okay, so here's that definition of inner product as matrix multiplication with the adjoint. Now we know that the adjoint is the adjoint of a product is the product of the adjoints in reverse order. And then we know that matrix multiplication, as long as we are consistent with our left to right ordering, is associative, right? So x adjoint a adjoint times y is the same as x adjoint times a adjoint y. Now this, as it turns out, is exactly the definition of x inner product a adjoint y. Okay, so the last thing we define this Hermitian matrix and come up with a specific theorem for that. A matrix is Hermitian if its adjoint is itself, so that's sort of an equivalent to being symmetric, just incorporates that complex conjugate as well. And a result for Hermitian matrices that I'll state but not prove is that A is Hermitian if and only if the inner product of ax with y is x times the inner product of ay for all x and y. So I'll just have you read this proof. It's pretty cool, but it's a super useful proof. It's a super useful property that we'll make use of later. Okay, folks, that's it for matrix multiplication. So again, we define matrix multiplication in terms of matrix vector multiplication. We talked about matrix multiplication by entry and saw tons of useful properties that result from that matrix multiplication by entry. Hope you enjoyed the video. Have a great day, and we'll see you next time. Bye-bye.